Okay. Hello guys. Very good morning. And that day abruptly current went off. That's why I couldn't join. My laptop got switched off. At least the internet was not a problem. Internet I could have arranged, but the laptop got switched off and the class got abruptly disconnected. Okay. And then actually after 15 minutes the current came back, but by the time you guys also left, so I thought it's okay. Fine. Anyways, so now let us start. Let me share my screen. So last class we were actually doing this, right? We were actually trying to understand this reversible and irreversible processes. If you can remember, we saw the form of graphs, what exactly is the situation, all these things, and then we did a derivation. We went for this exclusive thing called as isothermal reversible expansion of an ideal gas. Right? We saw that, right? Okay, now it is only for reversible expansion. It is only for isothermal process. This particular equation, W is equal to 2.303 RT log of V1 by V2, initial volume by final volume. And we already know that in case of an isothermal process, the first law comes out to be Q is equal to minus W because delta E is becoming 0. Right? So that is all about the final equation, and Q is equal to minus W. That is what you have to understand. That is what you have to remember, and nothing else. Right? And maybe the derivation also. Okay, but they shouldn't be asking you derivation because the integration knowledge is involved. Integration is not there for you yet, right? But still, you can just know it. It's very simple derivation only, right? Okay, so next thing what we'll do now is moving on to the next category. I'm going for adiabatic reversible expansion of an ideal gas. Okay, so we are going to do the same thing we did for isothermal. We are going to do the same thing for adiabatic processes now, right? So we know what happens in adiabatic process. In adiabatic process, there is no heat lost or there is no heat gained. All right. Okay, so now how will the first law look? I know first law says delta E is equal to Q plus W. Now I know in an adiabatic process, Q is 0. There is no heat change. There is no heat loss. There is no heat gain. So all that we'll have is delta E is equal to W. Okay, right? So now I know delta E. I know I'll be able to write it as NCV del T, and W. Again, we're talking about reversible work done. Right, so we have to use dV and stuff because we know we're talking about very small changes in volume, and I have to get the whole thing after integrating. That's what we do generally, right? So we will try to get a relation. We have to get a equation for the particular adiabatic reversible expansion of ideal gas, and I'll tell you how do we find the delta E and W. Okay, fine. So let us do this. Let us do this derivation. Again, derivation is not important, but it is little interesting. We'll see what exactly is happening. Okay. So now since we're talking about reversible processes, instead of using del T, let me use dt. Okay, NCV dt, let me write. Okay, because we're talking about a very small change, right? Because temperature is changing indeed. In this case, only the heat loss is not there or heat gain is not there. Okay, again, W, let me write it as minus P external dV, right? Minus P external dV. Okay, and then what we can do, we will be able to write this P external as, I know that we're talking about an ideal gas, so I can write pressure as nRT divided by V, right? nRT divided by V, correct? Yeah, okay. So now what we can have, we can rewrite this now. So I have NCV dt, right, will be equal to minus of nRT by V dV. Okay, nRT by V dV. All right. So now I can go for the integration. Now n is constant, CV is constant. So I have to integrate only for dt from initial temperature of T1 to the final temperature of T2. Right, from the initial temperature of T1 to final temperature of T2. Okay, now we have nRT by V. So I will be able to rewrite this as minus of nRT integral of dV by V. Right, because again, okay, fine. We should, one second, before we integrate, let us regroup the terms. Okay, right? So now what I'm doing is I just have to group these terms, T with dt and V is already with dV, but I just have to group your T with dt, right? And you can see that N and N will be cancelled. Number of moles will be cancelled both sides. Okay, fine. So all that we have is CV dt by T. Okay, CV dt by T is equal to R CV by V. Sorry, R RTK, so dV by V, sorry, right? CV dt by T is equal to a minus of R dt by V. Now I can go for integration, right? Now if you go for integration, right? Now you have to go for integration only for the variables, that is T and V, not for R is a constant, CV is also a constant, right? So from the initial volume of initial temperature of T1 to the final temperature of T2, initial volume V1 to the final volume of V2. That is what is the integration part, right? Okay. Now what we have? Now we know, I already gave you the formula. Integral of dx by x is ln x. If you can remember ln x, or we can even write it as log to the x base e, right? Okay. So we will be getting this. We will be we can do the integration now. Dt by t will become ln t. Dv by v integration will become ln v, right? So we can write Cv ln of t from T1 to T2 is equal to minus of R ln of V from V1 to V2. Okay, right? Fine. So now what we now we know what you have to do: upper limit minus lower limit. That's what we do. We substitute in the place of T2 first, and then in the place of T we substitute T1, and then take the subtraction. Same goes with V2 and V1. Upper limit minus lower limit. Right. So let us do that now. So CV into ln of T2 minus ln of T1, right? Ln of T2 by ln of T1, okay, which is equal to minus of R ln of V2, okay, ln of V2, right, minus ln of V1. No issues. It's upper limit minus lower limit. And I already gave you one relationship, log of A by B. We'll be able to write it as log A minus log B. Right now we have log A minus log B, log A minus log B. I'll be able to convert them into in the case of by terms of division. Right. So we can write CV into ln of T2 by T1. Right. And you understand that there's a negative sign inside. If I multiply the negative sign, it will become ln V1 minus ln V2. Right. So you will get R of ln of V1, ln of V1 by V2. Here it is T2 by T1. Here it is V1 by V2 because I have a negative sign inside. We'll multiply it inside. Right. That's what we have. Okay. So then what we have? Right. Now you understand that. Let me put it like this. Okay. See, you have one particular relationship, if you can understand. So we have log of A to the power B. Okay, we have log of A to the power B. If you have, how can you write this? You will be able to write this as B log A. Whatever is the power that will come here, and you'll be able to write it like this. Let's say, for example, log of 2 power 2 will be written as 2 log 2, something like this. Okay, so let us try to apply this particular thing here, right? So I can just rearrange these things to go like this. Ln T2 by T1 is equal to R by CV into ln of V1 by V2, right? So like this looks like this, right? A log B, right? So people, and one more thing, if this is going to become too much of logarithms, but I don't want to go. I don't want to confuse you. So people, this is what you will be getting. Okay, eventually you will be getting the equation like this: T1 V1 power gamma minus 1 is equal to T2 V2 power gamma minus 1. Okay, right? This is the equation which you will be getting. Don't worry about what is gamma and all. Gamma is nothing but in terms of R and CV. Right. So this is like taking anti-log on both sides. Both side log I have, I'll take anti-log on both sides and I'll do some manipulations and I'll be able to end up in this particular equation. Derivations is not important for you. Don't worry about it. Okay. So we will be getting T1 V1 power gamma is equal to T2 V2 power, T1 V1 power gamma minus 1 is equal to T2 V2 power gamma minus 1. Okay. Now, what is this gamma minus 1? Gamma minus 1 is nothing but R by CV. Okay, gamma minus 1. This whatever you're writing is nothing but R by CV. That's what you have here. It is going to come in the power. Right? So it's very simple to understand. Okay, right? So gamma by C, gamma minus 1 is what is called as R by CV. And this gamma is what is called as coefficient. It's called as something, no? Coefficient of. It's called, okay, it's called coefficient of thermal expansion. Okay, this is what is called as coefficient of thermal expansion. Okay, so gamma minus 1 is equal to R by CV. That's what you have to understand, right? And you already know one relationship between CP and CV, right? CP minus CV is equal to R. This relationship also, you know, May's relationship. So if I can just put it here, you will be able to get one more value of gamma. Gamma is nothing but CP by CV. This is another relationship you can remember, right? Gamma minus 1 is R by CV, right? What is gamma? Gamma is nothing but the ratio of heat capacity at constant pressure and heat capacity at constant volume. Okay, right? Fine. So this is the relationship you will remember. Okay. Now, how will you find the work done? How will you find the delta E? That is very simple. Say in the questions, they might give you say T1, V1, and V2. Right? They will give T1, V1, and V2. Right? So from this relationship, you will be able to find T2. Is it not? T1, V1, V2 is given. So you will be able to find T2. Once you find T2, directly we go for this relationship. Delta E is equal to NCV into T2 minus T1. That is delta T. Right? And you'll say, if you know value of T1 and you calculated the value of T2, obviously, you know, CV is constant, number of moles is there. You will be able to find the E. Right? And that delta E will be directly equal to W. This is how we do problems. Okay. In the question, they will not give you one temperature or something they will not give. That particular temperature has to be found out and put in the equation of delta E to find your delta E. And again, I know from adiabatic processes, delta E will be equal to W. And whatever is the delta E value, that is what is the W value also. Okay, right? So this particular relationship is very important, right? T1 V1 power gamma minus 1 is equal to T2 V2 power gamma minus 2, T2 V2 power gamma minus 1. Right now, this is in terms of temperature and volume. I can have, since I can go for ideal gas equation and actually manipulate it a little bit. I'll be able to get a relationship for pressure and volume also. P1 V1 power gamma will be equal to P2 V2 power gamma. See, the power is only for volume. Okay, the power is only for volume. Here also the power is only for the volume, not for temperature. Okay, again, you know what is gamma? Gamma is nothing but CP by CV. Or gamma, I can also write it as what? Gamma, I can also write it as R by CV plus 1 from this. Okay, anyways, right? So that is another relationship you can remember. P1 V1 power gamma is equal to P2 V2 power gamma, right? And we have another relationship between pressure and temperature, right? We saw temperature volume, pressure volume. Now we can have pressure and temperature also. So it will be P power 1 minus gamma, T power gamma. Oh, I forgot. What is this relationship? I think this is what is there. P1 power 1 minus gamma, T power gamma is equal to P2 power 1 minus gamma, T1 power gamma. Okay, but I would suggest don't use this. 99% you will not be using this equation at all. Mostly will be using only this equation. T1 V1 power gamma minus 1 is equal to T2 V2 power gamma minus 1. But it is just good to know all the relationships. Okay, right? So that is about your adiabatic reversible expansion of ideal. Yeah, tell me.
Could you show that relationship 1 second?
Yeah, sure.
Sir, it should be T2, right? And on the right hand side.
Yes.
Thank you, sir.
Okay, right. So people, these are 3 different relationships, but I would suggest you have to remember only this for the problem point of view, right? Because problems will come from this only. Other things, maybe you can just remember what are the relationships. That's it. Okay, right. So now we can do some problems. Let us do some problems. Oh, not complete. Okay, 1 second. Okay, take on the question. A gas is cooled. A gas is cooled and loses 65 joules of heat. A gas is cooled and it loses 65 joules of heat. Okay. In that process, work done on the system. In that process, work done on the system is 22 joules. In that process, work done on the system is 22 joules. Okay, right? So we have to find three things, right? You have to find Q, you have to find W, and you have to find delta E. Okay, right? So I'll repeat the entire question one more time. A gas is cooled and loses 65 joules of heat, right? And in that process, the work done on the system is 22 joules. Find Q, W, and delta E. They have not mentioned any type of process, adiabatic, reversible, nothing is mentioned. They have just told the situation, right? So we just have to use only one equation. What is this? Delta E is equal to Q plus W. This is the equation which you have to use now. First law of thermodynamics, right? Okay, now we have to be very, see, this question was given to you just to make sure that you know your sign conventions, right? So from the question, can you tell me what is the Q value? What is the
Sir,
Q value?
positive.
Heat is lost, right? Heat lost by the system is negative. Heat gained by the system is positive. Okay, so here the
Sorry,
value
work
is
is positive, sir.
work is positive because work is done on the system. Yes, good, right? So Q is minus 65 joules, right? Why? Because they're telling that heat is being lost by the system, right? Okay, now we know another thing. Work done by the system is negative, work done on the system is positive, right? So that here they're telling that work is done on the system, so that should be a positive value, and positive value of 22 joules plus 22 joules is what is the work done. That's it, right? So you already found out Q, you already found out W, right? Now can I use this equation to find delta E? Very simple. Delta E is equal to minus 65 plus 22, right? That's what we have from Q and W, and that's it. I think 65 minus 22 will become 42, 43, right? Minus 43 joules. That is what is your delta E. Very simple question. Very simple question. Right? So this question was given to you just to check your sign convention knowledge and nothing else. And the first law of thermodynamics. Very simple. Okay. Fine. Next question. Okay. A gas absorbs 200 joules of heat. A gas absorbs 200 joules of heat 200 joules of heat and expands by 500 centimeter cube, and expands by 500 centimeter cube against a constant external pressure, against a constant external pressure of against a constant external pressure of 2 into 10 to the power minus 5 Newton per meter squared, full stop. Okay, against a constant external pressure of 2 into 10 to the power, sorry, not minus 5 plus 5, 2 into 10 to the power 5 Newton per meter squared. Okay, you have to find the change in internal energy. Calculate the change in internal energy. That means delta E is what you have to find. I'll repeat the question one more time. A gas absorbs 200 joules of heat and expands by 500 centimeter cube against a constant external pressure of 2 into 10 to the power 5 Newton per meter squared. Find the change in internal energy. Okay, go for it.
Sir, I'm sorry, could you repeat the question?
Yeah, a gas absorbs 200 joules of heat and expands by 500 centimeter cube against a constant external pressure of 2 into 10 to the power 5 Newton per meter squared. Calculate delta E. Calculate change in internal energy.
Sir, delta V should be calculated in terms of meter cube, or can we keep it as
Yes.
centimeter cube?
Yeah, I want to answer in terms of joules. Okay, so you know that pressure into volume, I will be able to get joules if pressure is in Newton per meter squared and volume is in meter cube. That is normal SI units. If you have SI units, you will get the energy also in SI units, joules.
Okay, sir.
Okay, again, this is the same equation which you have to use. Do it. So people, I have mentioned like this, from this question, can you tell me whether it is going to be a reversible or irreversible process? This process, whatever is mentioning here, is it reversible or irreversible?
Reversible, sir.
Okay, how are you saying that?
Sir, because there's a const. Oh no. Wait.
Yes, you're looking at the correct word. So if I look at that phrase, what it means? It means
Sir,
it is
it's just expanding by the heat. No, sir. So it's nothing is like nothing irreversible is happening. So.
Look at this, people. I told you this, right? I mean, like if
Sir,
you
actually,
remember,
it's irreversible, right? Because it's constant pressure.
exactly, right? When we looked at the reversible and irreversible case, hope you remember. If this is an example for irreversible. The moment I removed the 10 kg, there was only one pressure, one constant external pressure. Okay, but in the case of reversible case, every time you remove the 0.1 kg mass, the external pressure keeps on changing, right? So we understood that. That is how we even plotted the graph. If you can remember, you are getting a plot like this for irreversible. Why? Because that is one constant external pressure in case of irreversible process. Okay, so the phrase which you have to look for is under constant external pressure, right? If they give you that particular phrase, it is understood that it is going to be an irreversible process, right? So in this question, they are giving you, right? Look at this. They are under constant external pressure of 2 into 10 to the power 5 Newton per meter squared. And it is understood that it is irreversible process. Okay. If they want to mention reversible, they
Sir,
will mention reversible. Yeah, tell me.
is the answer 100 joules?
Once again, what is the question? Okay, a plus minus anything?
I think it's plus 100.
Plus, okay, fine. Let us check. Right. So people, again, all that we have to use is this equation, L delta E is equal to Q plus W. Now Q is directly given to us. I think they said that the gas absorbs 200 joules of heat. So in this case, it is plus 200 because heat is getting added. Right. And we know W. W is nothing but minus P external into del V. Right. Now I told you this is in joules, right? So this has to be in joules, only then you can add them. This is in joules and this is in liter atmosphere, you cannot add, right? Both of them should be in joules. Okay. Now if at all you want to get the work done in terms of joules, you have to have SI units, as I mentioned. So you need to have Newton per meter squared for external pressure, and the volume should be in terms of meter cube. Okay, right. And hope you know what is the conversion between 1 meter cube and liters, right? So I think 1000 meter cube, centimeter cube is what is 1 meter cube. Huh? Yeah, correct. No, I think it's more. 10 to the power 6 will come. See, you can do it like
Yes,
this.
sir.
10 to the power 6 should come, right? Yeah, because 100 centimeter,
Yes,
or 10 to the power 2 centimeter is equal to 1 meter, right? So if I just cube on both sides, right, what will become? It will become 10 to the power 6 centimeter cube is equal to 1 meter cube. Okay, this is the conversion then, right? 1 meter cube is equal to 10 to the power 6 centimeter cube. Okay, right. So they have given 500 centimeter cube, right? How many meter cubes will come? Let us calculate like this. X should be 500 divided by 10 to the power 6 meter cube, right? So we can write it as 500 into 10 to the power minus 6 meter cube. That's what is the change in volume. Okay, see, they are telling you it is expanding by this much. That means they have already given you the change. The del V is directly given to us, right? It is changing by this much value, right? So delta V here, I can directly write it as 500 into 10 to the power minus 6 meter cube, right? It is given 500 centimeter cube that I'm converting into meter cube by multiplying by 10 to the power minus 6. 10 to the power minus 500 to the power minus 6 meter cube. Then you can directly substitute the answers now. So W, let us find it out first. P external is minus P external is 10 to the power 2 into 10 to the power 5 meter cube. Sorry, 2 to 10 to the power 5 Newton per meter square into 500 into 10 to the power minus 6 meter cube. Right. So now you will get the answer as how much? This will be 1000, right? So minus of 1000 into 10 to the power 5 into 10 to the power minus 6, right? So I think you will be able to write 1000 also as 10 to the power 3 into 10 to the power 5 into 10 to the power minus 6, all negative signs, joules, obviously, right? So 10 to the power, this is minus 1 plus 3 will become, minus 1 plus 3 will become 100, right? That is 10 power 2, right? 10 to the power 2 minus 10 to the power 2 joules. This is what is your work done. Okay, now you can substitute here. This thing already we know. So delta E is equal to Q. Q is plus 200, and the W value we got it as minus 100. That is 10 to the power 2, all in joules, right? So delta E change, we can write as 200 minus 100 is plus 100 joules. That's it. That's the answer to this question. Okay, simple form of tell me.
Sir, in the question it's given that it expands, sir, but what if the question was it is compressed? So the work done would be positive, right?
Exactly, work done will be positive.
So, but then how do we get that using the equation minus P external LV?
Like the formula is okay. So that you have to remember, in the sense that the whole formula is minus P external del V minus you have to put if the work is I mean if it is expansion, the work will be positive. Keeping that in mind, delta, it's all about delta V, isn't it? Right, depending on delta V sign only this will change, right? But in this case, delta V is not the value is given to us, but how much to how much they didn't give you. That's the problem. So for those, you have to remember, compression means it should be negative. Expansion means it should be negative. Compression means it should be positive. That's it. That's all you have to understand. The formula remains same. P external del V. That's it. But expansion positive, expansion negative, compression positive. That's it. That's all you have to remember. Okay. Right. So I hope everybody understood this question. Very easy only, right? Okay. Next question we will do. Fine. Next question. 1 mole of an ideal gas. What is the time? Okay. 1 mole of an ideal gas one second. Fine. 1 mole of an ideal gas underwent an isothermal reversible expansion. Underwent an isothermal reversible expansion from 1 liters to 10 liters. From 1 liters to 10 liters. Against a pressure of 1 atm. Wait. Fine. Anyways, just remove that part against the pressure of 1 atm. So I'll repeat the question from one more time. So 1 mole of an ideal gas underwent an isothermal reversible expansion from 1 liter to 10 liter under the temperature of 0 degrees Celsius. Under the temperature of 0 degree Celsius. Okay. Calculate the work done and the net heat lost or gained. Calculate the work done and net heat lost or gained. Whether it's going to be either gained or lost. That's why you're telling it's either heat lost or gained. How to find the Q value. Right. So repeating the question. 1 mole of an ideal gas underwent an isothermal reversible expansion from 1 liter to 10 liter under a temperature of 0 degrees Celsius. Right? You have to calculate W, that is calculate the work done, and the heat lost or heat gain, Q. So you have to find Q and W. Okay. So think about it. I can do this. So they have mentioned it as isothermal reversible expansion. You know which formula to use. right? So by this time, you're going to have at least figure out what is the formula. W is 2.303 nRT log of V1 by V2. And obviously Q and W are
So,
negative to each other. Yes, tell me.
sir, how do we calculate log of 1 upon 10?
Yeah, you can use log 1 is 0. Log 1 value is 0.
Sir, then what about log 10?
Okay, log 10 value is 1. See, okay.
Okay.
You can see in your exams you will be allowed to use your log books for finding out this. But if at all you don't want to use log books, let me actually give you the values, which is very, very easy to remember. Okay. Now, at least from log 1 to log 10, you have to know log 1, log 2, log 3, log 4, log 5, log 6, log 7, log 7, 8, 9, 10. You have to know at least these values for doing these kind of problems, right? Especially for JEE exams, right? Sometimes they might give you the log value in the question. Sometimes they might not give you, so you have to know it. But for your CBSE level exams, they will give you, they'll be allowing you to use the log books. So you'll be able to calculate from the log books, no issues. But anyways, so remember that log 1 is 0. I'm talking about log to the base 10, okay? Log to the base E values will again be different for all the numbers. Okay, we are talking about log to the base 10 only, not only here, in almost all the cases, we'll be using only log to the base 10. Okay, fine. So log 1 value is 0, log 2 value is 0.3010, right? And log 3 value is approximately 0.45, right? And then log 4, how can I write log 4? Log 4, you can write it as log 2 square. Is it not? And I told you relationship like this, log of a to the power b is nothing but a b log a. Is it not? The power will come behind, right? So you can write it like this, 2 log 2. I already know to log 2 value. Log 2 value is 0.3010, right? So you'll get log 4 value as 0.6020. Okay. Now log 5 value you have to remember, log 3 value you have to remember. Log 5 value will be approximately log 0.7 approximately. Okay, 0.7 approximately will be the log 5 value. Okay, next, log 6. Now I can write log 6 as log of 2 into 3. Right, I know relationship also. Log of a into b, I'll be able to write it as log a plus log b. So this one I'll write it as log 2 plus log 3. Right, log 2 plus log 3. Right, so log 2 plus log 3, that is 0.3010 plus 0.45. So approximately log 6 value is 0.75. Okay, approximately its value is 0.75 log 6 value. Okay, now log 7, you have to remember, okay, log 7 value is approximately 0.85, or you can even just keep it as 0.8 for calculation purposes. Log 8, how can I write log 8? 8 can be written as 2 to the power 3, log of 2 to the power 3. So again, I'll be able to write this as 3 log 2. Okay, so 3 into 0.301010, so approximately you'll get the value as 0.9 for log 8. Okay, and for log 9, right, approximately the value, okay, again you can calculate this, right? So we can write log of 9 as log of 3 squared, right? So again we can write it as log of see fine. This the exact value is actually 0.85. Okay, fine. We can keep it as 0.9, not an issue. Which is the top 3 log 2. Oh, log 2. 0.9 is okay. Fine. So now log of 9, you'll be it is 3 log square. So you'll be getting it as 2 log 3. Right. So it is approximately again going to be what? 0.9 only. So you can understand there'll be some differences here in the second decimals. Right. So log 8, log 9, approximately you can have 0.9, 0.9 only. Don't worry about the other decimals. These are just for rough calculations. Okay. And log 10 value will be 1. Right? Log 10 value is 1. Okay. So what log values you have to remember? Log 9, log 10 we have to remember, log 7 we have to remember, and log 5 we have to remember, and log 2 and log 3 and log 1. Right? Other things can be derived. Okay. Other things can be derived. Okay. So log 1 is 0, log 2 is 0.03010, and log 10 approximately important is log 10 is 1. Value is 1. Okay. So I think now you can do the problem without any issues.
Sir, is it approximately 52?
52, I don't know, I'll check. Right. So it's have to use this formula. That's it, right? So W first I can calculate 2.303, number of moles of gas is 1. And if at all I want the answer in terms of joules, right? If at all I want the answer in terms of joules, I have to use the R value accordingly. Right? R value should be 8.314 because I want the answer in terms of joules. If at all I want the answer in terms of calories, I would have kept the R value as 2. Okay, right? But now I want the answer in terms of joules, so let me keep it as R value as 8.314. Temperature is they have given 0 degrees Celsius. 0 degrees Celsius means I know it is 273 Kelvin. You should substitute the answers only in terms of Kelvin. Okay, right? Into log of V1. Okay, V1 is 1 liter. Okay, let me start out this entirely. Right, log of V1. Yeah, tell me.
Sir, here since we are using the volume in liters, aren't we supposed to use the value of R as 0.0821?
No. It is taken care of because even the volume by volume term getting cancelled, right? It's volume by volume. Are able to understand, right? It's V by V, right? The liters will get cancelled. So whatever
log A upon B is log A minus log B, right? So
yeah, okay, but still, eventually, however you do it, eventually the volume term is not there. That's all you have to understand because it is getting divided. Right. So whatever be the unit you are going to put, that is not going to affect your that is not going to in any way affect your R value. R value, whatever the unit you want in terms of for the work done, that value accordingly you will put, because this is going to get cancelled, both the volume terms. Okay.
Okay, sir.
Right. So let me run this. What happened? Okay. So we have V1 by V2, that is log 1 by log 10, because initial volume of 1 to final volume of 10 liters, right? So now what we have, so we have W is equal to 2.303 into 1 into 8.314 into 273 into log 1 minus log 10, right? So you will be getting log 1 value is 0, log 1 value is 1, log 10 value is 1, that we already know. Right, so we just have to have a negative sign. Minus 1 is only remaining. So overall, the value is minus 2.303 into 8.314 into 273. Right, so I think you have to do the calculation properly. So this is approximately 2.3. I think you like exact value. Can someone tell me? Use your calculators, people. But in your exams, please don't use. Wait, where is my calculator? Okay, so we have 2.303 into 8.314 into 273. Yeah. So we are
Sir, 5227.
yeah, that's what 5227 approximately joules. Okay, or you can also write it as 5.227 kilojoules. Right, this is also okay for me. Right, 5.227 kilojoules or 5227 joules. That is going to be the answer. Minus, obviously, minus. Right. So if this is the W value, what is the Q value? Q value should be negative of this. So that Q value would be plus 5.227 kilojoules would have been your Q value. Okay, right. Right. So that is about this problem. Very easy problem. That's one direct one formula substitution. Right. Okay. Right. I hope everybody's copied. Everybody is okay. Right. Any please any note, please ask me. Right. Next question. Right. 2 moles of an ideal gas. 2 moles of an ideal gas. 2 moles of an ideal gas underwent an isothermal reversible expansion. Underwent an isothermal reversible expansion. At 298 Kelvin. At 298 Kelvin. From 1 bar, from 1 bar to 0.66 bar. Okay, from 1 bar to 0.66 bar. Calculate the work done. Calculate the work done. Okay, right. So people, in this question, I have not given volume at all, but in the formula we need volume, right? V1, V2 we need, but all that we'll have is this is the pressure, initial pressure of the gas, this is the final pressure of the gas. P1, P2 is what we have, right? So, and they are given as an ideal gas also, right, people? So remember that like we can use your Boyle's law. What does Boyle's law says? P1 V1 equal to P2 V2, right? So if at all I want to get V1 V2, that is nothing but P2 by P1. This is the relationship we'll be using here. Okay, so you can rewrite the particular formula which I'm telling you, that is 2.303 nRT log of, instead of V1 by V2, what will you put? P2 by P1. That's it. This is another formula which you can remember. But this pressure which you're talking, this is the pressure of the gas. Pressure of the gas, not the external pressure. Okay, we're talking about the pressure of the gas. Okay, right? Yeah, all that you have to do is substitute and get the answer. Okay, so I don't think you have to go for the log calculations or not. Just substitute everything, whatever you know. Okay, 2.303, number of moles is 2, R value is 8.314, temperature is 298 Kelvin, log of P2, initial final pressure is 0.66 from the initial pressure of 1. That's it. Okay, right. So I can actually do this log calculation without even log book. Okay, let me tell you how to do this. See, this is nothing but log of 0.66, log of 1, log of 1 is 0. Don't worry about it. So log of 0.66, can I write this as log of 1 by 6, people? Right? What is 0.66? 0.66 I will be able to write it as 1 by 6, 1 by 6 and even 0.66. right? So again, this I will be able to write it as log 1 minus of log 6, right? So I know log 1 is again 0. Log 6, how can I write? Log 6, I can write it as log of 2 into 3. So that would be nothing but log 2 plus log 3, right? Log 2 value is 0.3010. Log 3 value is 0.45. So log 6 value is approximately 0.75. That's it, right? So now
sir.
what you have to do? Log of 0.66 is nothing but minus. There should be a minus sign. I'm so sorry. There's a negative sign
Sir,
also. Yeah, tell me.
sir, 1/6, isn't it 0.1666? Like not 0.66.
Okay, yes, it is not 0.666. It's 0.16666. Correct. 0.666, then how can you write? Maybe we can write this as, we can write like this, right? 0.66, right? I will be able to write it as log of 2 into 0.33. Okay, and I can write this as log 2 plus log of 0.33. Okay, and I can write this one log 2 plus log of 1 by 3. Now this is okay, right? Now again I can do the same thing. So it will be log 2 plus log 1 minus log 3. That's it. That is nothing but log of 0.66. Okay, every value you know now, right? Log 1 value is 0, right? So this is going to be log of 3010. This is going to be log of 0.45. So 0.45 minus 0.3 will become minus 0.15 approximately. This is what is log of 0.066, I mean 0.666. That's it. This is your value. Okay, so if you're little good at mathematics, like you don't need log tables, you'll be able to do it yourself. But again, you have the luxury of using your log tables in your exams, so don't worry about it. Okay, so you can substitute the log value of 0.66 as, sorry, log of minus 0.15, and you'll be able to do the calculation easily and get the answer. Okay, right? Okay, fine. Next question. What is the time? Okay, fine. Maybe, or we'll take a break. I will take a break, and after time is 12:23. We'll meet by 12:33. Okay, or we'll meet by 12:35. Okay, we'll resume the class by 12:35. I will be here only, and I'll be just muting myself and shooting a video. Okay, so we'll meet by 12:35. You can go for a break of almost 10 minutes. Right. Okay, I hope you guys are back. I guess back. Shall we start?
Yes, sir.
Okay. Right. So next question. So they have given you this diagram. Okay, they are telling that I have 10 liters and 300 Kelvin. It is moving to some V liters 150 Kelvin. Okay, and they're given that I'm taking 1 mole of CO2. Okay, right? So you have to calculate what is V, and they have given one more thing also, Q is equal to 0. Okay, right. So first is the from what? Okay, can someone tell me what and all you can understand from this diagram? What and all are the things you'll recover from this diagram? Then we'll try. Once you
Sir,
find out what, yeah, tell me.
Sir, I think the gas is getting expanded under constant temperature.
Under constant temperature?
Oh, no,
Temperature?
no, sorry, sir. Sorry, sir. It's changing. No.
The clue is this. When, in which kind of process Q is 0? In which kind of processes Q is 0? That means there is no heat loss, there is no heat gain. What kind of process? Really? Thinking this much? When in which kind of processes heat is no heat is lost, no heat is gained? Q is 0. Which kind of process? Adiabatic, right? People, what happens in adiabatic process? There is no heat loss, there is no heat gain, Q is 0. So we can directly write delta E is equal to W. Yes, right? So this is a case for reversible, or say adiabatic reversible expansion. Like I don't know expansion, but definitely it is going to be expansion only because temperature is getting reduced. So you understand that it is going to be adiabatic reversible expansion of an ideal gas. I mean, you have to assume that CO2 is an ideal gas. Okay, CO2 is not an ideal gas, but you have to assume that it is actually going to be an ideal gas. Okay, so whenever Q is 0, whenever this is given to you, then you have to understand that that is nothing but an adiabatic process. Okay, right? So now they are asking you to find the volume. This volume, what is the final volume they want you to find? Right? So now how will you do this, people? How will you do this question? Adiabatic reversible expansion, we know the equations, right? What is the equation for T and this is temperature and volume, both are changing. So we have this, right? T1 V1 power gamma minus 1 is equal to T2 V2 power gamma minus 1. Right? Okay. So we can substitute here. Yeah, tell me.
Oh, sir, sorry, I got disconnected. There was a power cut. Could you just repeat what you said?
Yeah.
About the question?
Sure. What I was telling is, in which kind of process Q is 0? Obviously, it is going to be only an adiabatic process, right? In adiabatic process, there is no heat loss, there is no heat gain, right? So if Q is 0, I'll be able to manipulate your first law of thermodynamics mathematical form into this one, right? Delta E is equal to W. Very simple, right? So basically, what are they trying? They're indirectly telling you that this is an adiabatic reversible expansion of an ideal gas. Even though CO2 is not an ideal gas, we have to consider it as an ideal gas for now. Okay, so you have to find the final volume. That's what is asked. They wanted to find the V. That is the final volume. What is the final volume? It is getting expanded to, right? So whenever we have adiabatic processes, we have this kind of equation, right? T1 V1 power gamma minus 1 equal to T2 V2 power gamma minus 1, right? So we can substitute the values now, right? Initial temperature was 300, right? The volume was 10 liters. Power gamma minus 1 is equal to final temperature is 150 Kelvin, right? And the final volume is V. That is what we have to find, gamma minus 1. Right? Now, how will you find gamma is another question, right? I know gamma minus 1 is nothing but R by CV. Hope you remember this. Okay, gamma minus 1 is equal to R by CV. Just now we derived. Is it not? Right. So R value is okay, right? I want to find the CV value. Now CV value is not directly given to you, but I know CO2 is a polyatomic gas, right? So CV for polyatomic gases, I know it is nothing but 5 by 2 R. Like I told you, it is 7 by 2 R, right? But most of the cases, right, depending on except for very few cases, normal gases what we have, they will have CV value as 5 by 2 into R. Yeah, we already know this, right? So the CV value for CO2 gas is nothing but 5 by 2 R. That is what we have. Okay, right? So now you can find the gamma minus 1. So gamma minus 1 is nothing but R divided by 5 by 2 into R, right? Divided by 5 by 2 into R. That is, so if this 5 by 2 goes up, RR gets cancelled. So gamma minus 1 is nothing but 2 divided by 5. Okay, gamma minus 1 is nothing but 2 divided by 5. Right? Okay, that's it. We know everything. All that you have to do is substitute and get the answer. So we have 300 into 10 to the power 2 by 5, right? 10 to the power of 2 by 5 is equal to 150 into V to the power of 2 by 5. That's what we have, right? Okay. 2 by 5. How do we calculate? 10 to the power 2 by 5. Are we using the C value? 1 second. I'll just close the door and come. Okay, so this, are we doing it? Just one moment, people. Just one moment. I'll just confirm whether we are doing it correctly. $1.33. What is the CV value you have to substitute? Once again, I have to. The CV values are a problem. Okay, let me check. CV for CP by CV for CO2 gas, carbon dioxide specific heat. Okay, for a monatomic gas, it is 3 by 2 R. For a diatomic gas, it is 5 by 2 R. For a polyatomic gas, Okay, for a monatomic gas, it is 3/2R. For a diatomic gas, it is 5/2R. And for a polyatomic gas, it is 7/2R. Okay, what I told was correct only. But why in this case then, why have they put it as 1.33? Okay, not sure what is happening here. So if you use it as 3/2R, then I will be getting it as 3 divided by 2, right? Gamma minus 1 will get it as 0.3. No, 3/2 will be 2/3 would 2/3 would be
0.66.
yeah 0.66, and we'll be getting it as some problem. Okay, so people, instead of remembering all these things, the thing which I'm seeing constantly is that the gamma, right? Gamma value for a polyatomic gas. We'll state. I'll anyways tell you how exactly this is happening. Okay, so remember that gamma value for a polyatomic gas is 1.33. Always remember this. Okay, for a polyatomic gas, gamma value is 1.3. This is a constant value you can always use. Okay, right? So gamma value for a polyatomic gas is 1.33. So if that's the case, let us rewrite this again. So if gamma is what to say 1.33, gamma minus 1 should be 0.33. Hope you're able to get this, right? So gamma value is 1.33 for a polyatomic gas. Gamma minus 1 would be 0.33. So let us substitute it. So gamma minus 1, gamma minus 1, gamma minus 1 is 0.33, right? And this value is also going to be 0.33. Okay, right, fine. So now what we have to find is this V is what we have to find. Okay, right. So we can write it like this, right? Say V divided by 10 the whole to the power 0.33, right? This is not 1.50, this is 150. Okay, so V divided by 10, I'm just bringing it here, the whole power, this thing. So 150 will go here, that will be 300 divided by 150, which is nothing but 2. Okay, so now see, remember, and you can do one more thing, like you don't have to go for calculators and stuff for calculating this particular thing. This 0.33 is nothing but 1/3. Is it not? 0.33 is nothing but 1 divided by 3, right? So I can write this here, right? So V divided by 10, but the whole power 1/3 is nothing but 2. That's what we are getting here. Right? So what I can do, now this is nothing. Whenever I write power 1/3 means what? This is nothing but cube root, right? Cube root of x is nothing but x to the power 1/3. Okay, cube root of x is nothing but this power x power 1/3. Okay, and whenever we write square root of x, that power is what? That power is going to be 1/2. Okay, x power 1/2 is nothing but root of x. Okay, right? So here it is 1/3, so it is cube root. Okay, so now what I can do, I don't want this cube root, so can I whole cube on both sides, right? Can I whole cube on both sides? So when you do the whole cube, 3 and 3 gets cancelled, so all that I'll have is V by 10 is equal to 8, that is 2 cube, right? So the final volume should be around 80 liters. That's the answer to this question. Okay, right? So like you have to remember two things. First thing you have to remember is this polyatomic gas gamma value is 1.33. So gamma minus 1 would be 0.33, right? And then remember that whenever I get 0.33, I'll be able to write it as 1/3, right? 1/3, something power 1/3, nothing but the cube root. So to overcome the cube root, I just overall cubing on both sides so that the 3 gets cancelled. So you'll be able to get the final volume links. Okay, 80 liters. That's the final volume. Okay. Right. So let us do another problem like this. Okay. So they have given a similar kind of thing. 300 Kelvin, 100 decimeter cube, U is equal to 0 to T Kelvin, some T Kelvin, 800 decimeter cube. Okay, so you have to find the work done, right? What is the work done? Okay, we're talking about which gas? We're talking about 1 mole of ammonia, NH3. Okay, you have to calculate the work done, right? So obviously we understand that W and delta E are same for an adiabatic process, right? So if I can find what is delta E, and that value is only W, correct? And I know what is the value, what is the formula for delta E? Delta E is nothing but the NCV del T, right? So that is nothing but NCV T2 minus T1, right? T1 I know already, 300 Kelvin. If I can find what is this final temperature, then I'll be able to substitute here and find your W values. Okay, and find your W values. Very simple. Right? Go for it.
Sir, here we use 7/2R, right? CV value for.
No, like directly you can use the gamma value directly you can use. This is again a polyatomic gas. Gamma value of ammonia is again 1.33. That's it. The CV value which you have to use here. Yes, this value would be 7. I think you have to use it as. I think you have to use it as once again. CV value, what are they doing? Minus 3. Yeah, you can use the 7/2. This is correct. 7/2 R. Okay. And people, I want the answer in terms of calories. I want this W in terms of calories. Any answers?
1 minute.
Okay.
So is it minus 1050?
I don't know. We'll check.
Minus 1050 joules.
Okay. Okay. Fine. Joules. I said I wanted in terms of calories, but okay, no issues.
Oh, sorry. Calories only, sir. Calories.
Okay. Fine. Right. So again, this equation T1 V1 power gamma minus 1 equal to T2 V2 power gamma minus 1 is what is the formula we have to use, right? So T1 is 300 Kelvin. Initial volume was 100 decimeter cube, the whole to the power gamma minus 1. Gamma minus 1 is 0.33 because gamma value is 1.33. Gamma minus 1 is what you have to use. Okay. T2 is T Kelvin, right? Into final volume is 800 whole to the power 0.33, right? Okay. So let us club the terms together, right? Or I can write like this. T is equal to 300 into 100 divided by 80, the whole power 0.33, I'll write it as 1 by 3 again. Okay, 0.33 again, write it as 1 by 3, right? So you have just 1 divided by 8, right? So there's nothing but cube root of 1 by 8, right? Temperature is nothing but this into cube root of 1 by 8, anything. 1 of cube nothing matters. So I know cube root of 8 is 2, right? So all that we'll have is 300 into 1 by 2, that is 150 Kelvin. That is your T value. Done. Okay, that's it. Now all that you have to do is substitute in the formula. Now you find the final temperature, also initial temperature we know. So delta E will be equal to W, and that will be equal to NCV delta T, right? And I can write this number of moles is 1 only. CV is 7 by 2. R. Now since I want the answer in terms of calories, I'll use the R value as 2. Sorry, R value correct. R value as 2, right? So remember, CV for any polyatomic gas is 7 by 2 into R. That's what I'm using here. R value, where R value here in this case is 2 because I want the answer in terms of calories. Okay, into T2 minus T1. So it would be T2 is 150 minus initial temperature was 300. Okay, 300 initial temperature, right? So obviously 2 will get cancelled. Here you will get some 200. Sorry, 150 into 7. Okay. 150 into 7, 150 into
1050, sir.
yeah, 1050, right? So minus 1050 calories. That's the answer to this question. Okay, simple questions only, right? Okay, people, I think that is enough number of problems we did, right? Quite a good amount of problems we did, and all the formulas which you have done, we have used it now. All right, what is the time? We have half an hour. Okay, cool. So that is all about the problems, right? Now we are going to delve into some another interesting topics. Right. Okay. So people, I am going to introduce you to this particular term now. Right. The term which I want you to get introduced to is entropy. Okay. Right. So this is thermodynamic quantity. Okay. This is also like how you have work, how you have what to say Q, how you have delta E. Like that, we have something called as entropy, which is denoted by the letter S, capital S. Okay, right. So what exactly is this entropy, right? This see, we will be able to get a lot of insight about why only a certain process happens like this. Say, for example, why is it that say when the waterfall happens, it is always coming from top to bottom? Why is it not going from bottom to top? Right? Why only heat goes from hot body to colder body? Why is it not going from colder body to hotter body? Right? And say why is it that whenever boiling happens, its expansion is happening? So all those normal things, why, all those questions of why, you will be able to understand only if you study about entropy. Okay, right. So what exactly is entropy? In simple English words, I will be able to tell about this entropy as that it is going to be a measure of randomness. Okay, it is a measure of randomness, right? So how random a particular species is, how like, or in other words, right? Entropy can also be a measure of disorderliness. Orderliness, we know everything is properly ordered. Disorderly means completely random, right? Or I can also tell that it is actually going to be measure of chaos. What is chaos? Everything going to haywire, like everything chaotic, we say. Right? So this entropy is nothing but the measure of randomness. How random something is that say, how to put it? Something random means like, say, so I'm little very calm. I'm sitting like this, right? I will tell that I have lesser entropy, but I'm very, very active, moving around, playing, running, and all these things. I will tell that I have high entropy. Okay. So the amount of randomness increases, the entropy. Is someone has asked a question? Okay, right. So this is all about the measure of randomness, how random that particles are moving, how random we'll be able to arrange these things, like all based on that, right? That is nothing but your entropy. Okay, measure of chaos, right? So like the definition seems little weird. What measure of randomness? But yeah, that is going to make a lot of sense to you, in a while. Okay, right. So that is the definition for entropy. Okay. Right. What is the mathematics? What is the mathematical relationship between entropy? I mean, how you can get a mathematical formula or say mathematical formulation for entropy? This S, entropy, is equal to Q. This is how we define it. Okay. In thermodynamics, say you can ask me, sir, is there any derivation? Is there any proof for whatever I'm writing here? No. This is how it is defined. Right? Mathematically, this is how it is defined. Right? There's no other way of defining it. Okay. So this entropy is nothing but Q divided by, Q reversible. Okay. This REV represents reversible. Okay. So whatever be the type of process we are going to do, we are going to assume it to be reversible processes. Okay. Anyways, so the heat lost or heat gained at the reversible process, during a reversible process, divided by the temperature, absolute temperature. In Kelvin, obviously. This should be in Kelvin. This is how we mathematically define entropy. Yes. Okay. Right. So now you can understand that imagine it like this. Okay. Or okay, this is actually not S. This is delta S. Okay. Absolute entropy will not be able to find. Right. Okay. So people, please understand that you will not be able to measure the absolute entropy. That is the absolute S value. You will not be able to measure it because it doesn't make sense at all, right? How do you say, this is like, say, this much is the randomness? like will not be able to make, like, it doesn't make some sense, right? But I can tell if I do some process, right? If I do something, I will be able to change the value of entropy. I'll be able to change the amount of randomness, right? How much is the change that you will be able to calculate. Okay, that is what is delta S. So we will not be just like how we had E. I told you that absolute value of E cannot be found out. Only the change in E can be found out. Same way, absolute value of S cannot be found out. Only the change in S, that is delta S, can only be found out, and that is defined by this formula. Okay, there is no derivation, there is no nothing. This is how it is defined. Okay, Q reversible by T in Kelvin. Okay, now people try to understand this. Okay, say when I go for, say something is at some temperature, say 25 degrees Celsius. Okay, now if I increase the temperature, let's assume that I have a gas. Okay, I have a gas which is at 25 degrees Celsius. Okay, and say I'm increasing the temperature of the gas to say 100 degrees Celsius. Right now, what do you think will happen? Obviously, the gas molecules will be already moving here, right? And if I increase the temperature, they'll be moving very fast, right? They'll be moving more randomly, right? So we understand that here there is more entropy, here there is less entropy, right? Here there is more entropy, and here there is less entropy. Okay, so that you can understand what exactly is happening. If the randomness increases, if the unpredictability increases, then your value of delta S also increases, or say the entropy value increases. Right? Okay. So anyways, this is how it is defined. Q reversible divided by T. Okay. Now I'll be able to tell certain things about entropy. When I compare a solid, liquid, and a gas, when I'm talking about the solid, liquid, and gas, right? In general, say H2O in solid phase, H2O in liquid phase, H2O in gaseous phase. I have. Okay. Now, if I ask you which is going to have more entropy, which is going to have lesser entropy, you can always just close your eyes and tell that gaseous substances will always have maximum entropy, because they are the ones which will be moving, right? They have maximum kinetic energy. They'll only be moving. In solids, almost it is zero. There is no movement at all. Liquids, little movement is there, right? So always remember, people, gaseous molecules, more and more gaseous molecules you have, more and more will be the entropy than the liquid molecules, than the solid molecules. Okay, gases will always have maximum entropy. So yeah, and solids will have always the minimum entropy. Okay, right? And any other thing? Say, okay. Now, if at all I talk about gases, I talk about different gases, right? So generally we can say the atomicity of the gas. The atomicity of the gas is directly proportional to the entropy value, right? Because we understand why. Right? Because we understand that in case of a monoatomic gas, only one type of motion is possible, translational motion is possible, right? But diatomic gas, translation as well as rotation is possible. In polyatomic gas, more, that is translation, rotation, and vibrational motions are possible. So there is more unpredictability there, right? So that is why we say atomicity of a gas is also going to be directly proportional to the S. So for example, if you have to consider helium, hydrogen, and say H2O gas, definitely H2O will have maximum entropy than H2 than helium. Right? Because this is monoatomic, this is diatomic, this is polyatomic. Okay, right? So like this, we'll be able to compare. Hope now you're able to get an idea what exactly are we talking about in case of entropy, right? It is all about how much randomly things are moving. All right. Okay. So based on this particular thing, based on the entropy, right? What is the time? Okay. Based on this particular entropy, that is where we actually go for definition of second law of thermodynamics. Right, the second law of thermodynamics is actually entirely based on this particular term, entropy. Okay, right. Take down a statement, people. Take down a statement. A spontaneous process is the one in which the entropy. Oh, wait. Guys, well, just rub whatever, just strike it out whatever you wrote. Okay, strike out everything. Right, I'll repeat it again. Okay. the direction of the spontaneous process, the direction of a spontaneous process is going to be in such a way, that the entropy of the universe, such that the entropy of the universe is increasing. Okay, that is the law. Again, I repeat the statement. Okay, the direction of the spontaneous process should be in such a way that the entropy of the universe should be increasing. That's a very simple statement. Okay, now people, first of all, we have to understand, what do you mean by a spontaneous process? Okay, what do you mean by a spontaneous process? A spontaneous process is one which is going to happen on its own, right? Which is going to happen on its own. What do you mean by happen on its own? We don't have to do anything for the process to happen, right? The process will happen on its own. That's what do you mean, right? What do you mean by happening on its own? Again, in terms of energy, you can speak, right? So you do not have to spend energy for the particular process to happen, right? Say for example, I take a piece of sodium, okay, and I put it in water. That's it. Now I just have to keep sodium and H2O in contact, and eventually the violent reaction will happen. Whatever the products will get formed, right? So that is an example for a spontaneous process, right? You understand that you just have to keep them in contact and nothing else, no energy spent, nothing else. So this is an example for a spontaneous chemical reaction, right? Say spontaneous process, what I can tell, say heat moving from a hotter body to colder body, you are not doing anything, you're just keeping them in contact, eventually heat will flow. You are not doing anything for the process to happen, right? Say the waterfall, in the waterfall always water goes from top to bottom, not from top to bottom, bottom to top. Why? Because that is what to say, that is a spontaneous process, because we understand that we are not doing anything. Water only naturally it comes down by itself, right? So these are all the things you have to understand about spontaneous processes. We do not have to do anything for the process to happen. When I say we do not have to do anything for the process to happen, I am telling in terms of energy, right? We don't have to spend energy for making the process happen. The process will happen on its own. Okay, so now the second law of thermodynamics talks about what is the condition for the process to be spontaneous, right? Okay, this process I'm going to call it as spontaneous, right? What is the condition for a particular process to be called as spontaneous or not, right? So the second law says that for a spontaneous process, the direction of a spontaneous process, or for a spontaneous process, it is telling that delta S universe, the universe is change in entropy, right, should be greater than zero. That is, the entropy of the universe should increase by doing that process. Okay, if at all there is a spontaneous process, and if at all that is going to happen, it will happen in such a way that the universe is changed in entropy, or say the entropy of the universe is going to be increasing, or I can tell the delta is universe. That is, a change in entropy for the universe should be greater than zero, positive value. That means the entropy is increasing. Okay, that is exactly what is the definition for a spontaneous process according to second law of thermodynamics. Okay, right. So we are not talking about system, people. Here we're talking about universe. So be very careful. Delta is universe, right? That would be equal to, again, what you have to take the system as well as surroundings, right? Because I know system plus surrounding is what is your universe. What is wrong? Okay, right? So we are going to have delta S of the system plus the delta S of the surrounding. Okay, when you add them both for a spontaneous process, then you will get your delta S universe. That value should be greater than zero. We are not talking about this. We are not talking about this. We are talking about the sum of this, right? If you take the sum of that and you calculate the entropy of the universe, right? Now that value, if you find to be greater than zero, then we can call that particular process as a spontaneous process. Okay, that as a spontaneous process. Okay, right? So maybe let us try to understand. Maybe let us take some example. Okay, let us take some example for us to understand what exactly is happening here. How is it that the, what to say, that particular, for a spontaneous process, we are going to have delta S universe to be greater than 0. Okay, but before we move on to this, right, before we move on to this proof of how exactly this is happening, I want to introduce another thermodynamic term to you. Okay, I want to introduce another term to you, and that is enthalpy. Okay, this enthalpy is denoted by the letter H, capital H. Okay, now how do we define enthalpy? Right, so this enthalpy this is very similar to internal energy. Okay, this is very similar to internal energy. So if you can remember, internal energy, I actually define it as QV. What is QV? QV is nothing but heat lost or gained at constant volume. Right, that is how you actually got the equation also. The delta E is equal to NCV delta T. We got this by defining this heat lost or heat gained at constant volume as only the delta E. Okay, so enthalpy is also going to be very similar. So what are we going to do is we are going to define the change in enthalpy, or say the enthalpy is nothing but heat lost or heat gained at constant pressure. Okay, heat lost or heat gained at constant pressure. All right, so this QP, how can I write this QP? I mean, how can I, this is nothing but heat lost or gained at constant pressure. Okay, that is how we define your enthalpy, change in enthalpy, delta H. Okay, so now I know overall Q will be equal to QV plus QP. Is it not? Overall Q is nothing but QV plus QP. Right, so I know QV, I will be able to write it as NCV del T, and QP I will be able to write it as NCP del T. Right, so now again I'll be able to get a beautiful relationship for delta H. Now delta H is equal to NCP del T. Like how you have delta E is equal to NCV del T, delta H enthalpy is actually going to be what is that? NCP del T. Okay. Right, so that is again nothing but some kind of heat, but which is going to heat loss or heat gain by what condition? At constant pressure conditions. Okay, so if I go for an isobaric process, right, if I go for an isobaric process, what is isobar? Iso means, okay, iso means same, right? Bar means pressure. So isobaric process is a process where the process happens under constant pressure conditions. Okay, isobaric process is where it happens under some constant pressure conditions. Okay, right. So now what is going to happen? We can write delta E is equal to Q plus delta E is equal to Q plus W. Right, now this Q is now going to be QP. Right, so we can also write this relationship as whenever we have isobaric process, delta E will be equal to delta H plus W. This we'll be able to write for an isobaric process, because now Q is what? Q is now going to be heat lost or heat gained at constant pressure. Is it not? Now that QP is nothing but delta H. Okay, so for an isobaric process, people, this is how the equation will look. Delta E is equal to delta H plus W. Okay, let me actually plug in the charger once again. Okay, right, so delta E is equal to delta H plus W, because that is what the QP, that is the heat loss or heat gained at constant pressure, is how we define your delta H. Okay, now you will be able to get a relationship between your delta E and delta H depending on what is the W, right? Fine. So people, please understand, when we talk about the difference between delta E and delta H, obviously one is heat loss at constant volume, another one is heat loss at constant pressure. Is it not? Now that is obviously going to be based on this work done. Right, now please understand this difference is almost zero. Is almost zero for liquids and solids. Okay, right? Why? Because the change in volume or change in pressure for liquids and solids are very less. Okay, so there is utterly no difference between your enthalpy and your internal energy change between for liquids and solids, right? But for gases, right? But for gases, you indeed have some good difference. Okay, you have a like concrete difference between the value of delta E and delta H for gaseous molecules. Okay, right? So how do we do this? Let me see. Right now, W you will be able to write it as minus P external del V delta E minus delta H. Delta E minus delta H, I'll be able to write it as minus P external del V. Okay. Then what we do, we write it as delta Ng RT. Yeah, we can directly write it as delta Ng RT, right? Okay, right. So we already derived the relationship. If you can remember, P del V, we wrote it as what? Delta Ng RT. Right, delta Ng RT. No, but there is another relationship, no? Delta E and delta H. 1 second, people. Just give me one moment. Okay, whatever I'm writing is correct. Right. Okay. Right. So now we have already derived this relationship, right? That P delta V is equal to delta Ng RT. Right. So now I can substitute it here. Okay. Delta E minus delta H is equal to minus delta Ng into RT. This is the relationship, and I already know what do you mean by this particular thing. That is delta Ng means I know what is this. For example, if I have a reaction like this, maybe I'll give you the reaction just given you. This is a good example. That was it. Okay, so if I take this particular reaction, C6H6 in liquid state plus 15 O2 in gaseous state, right? And then that is going to give you 12 CO2 in gaseous phase plus 6 H2O in liquid phase. Okay, now if I want to calculate what is delta Ng, we know what is delta Ng, total stoichiometric coefficient of gaseous products minus total stoichiometric coefficient, total stoichiometric coefficient of gaseous reactants. Right? Okay. Now you have to take only about gases. We have to talk only about gases, and we have to define this value. So delta Ng in this case would be equal to, now in the product side, we have CO2 as the only gaseous product, and the stoichiometric coefficient is 12. Right, and in the reactant side we have only one gas. Again, these two are liquids, right? So to consider only about gases, so that is having a stoichiometric coefficient of 15. So in this case, the delta Ng value is -3. Okay, like this only we calculated delta Ng. Okay, so definitely you will have since why are we not taking liquids and gases, as I told you, because their change in volumes or change in these things are not going to be significant. They're going to be very less value. So eventually we can tell that enthalpy and internal energy values for solids and liquids are almost same, right? They're same, but for gases they are indeed different, and that exact difference is what is given here, minus of delta Ng RT. Or you can also write it like this: delta H minus delta E is now, you can just change the sign. Now it is going to be equal to delta Ng RT directly. Also you can write it like this. Okay, this is fine, right? Delta E minus delta H is minus delta Ng RT, or delta H minus delta E is delta Ng RT plus delta Ng RT. That is it. And whichever you want, you can remember. Okay, and we can also do problems based on this. So why did I introduce this particular enthalpy is because, again, it is going to be useful for proof of this particular thing. When I told you about delta S universe should be greater than 0 for a spontaneous process. Okay, but I don't want to take it up now, right? We'll see it in next class, because I have to introduce you sort of in some other things also, and then I have to do this. Okay, If there are no questions, we'll be able to end up the class. Is there any other question? Any question anybody wants to ask me? Any particular questions? Okay, if that's the
Sir?
case. Yes, Kana, tell me.
Sir, Gibbs free energy we'll see next class.
Coming. In second law of thermodynamics only, we'll see. It is going to be related to enthalpy, entropy, everything. We are going to relate it now after some time in second law of thermodynamics only. Okay. Maybe next class we'll be doing it. Yes. Okay. Right, people. Any other questions anybody has? Fine. Okay. Thank you so much, people. We'll meet again next week.